Now we're going to define yet another kind of integral. In this case, the domain of integration is actually going to be a curve in space. So let's say that curve is given in the familiar way as a position as a function of t, where t ranges from a to b. So in order to do this, we're going to use arc length along the curve. So the way this works is, remember that the rate of change in the arc length as you walk along the curve is your speed. And the speed is the magnitude of r prime. It's a scalar. Right? So this just says the change in distance along the curve is equal to the speed. And then with that definition, or with that in mind, I should say, we write down a definition. So we call this curve here now just c. And then we have an integral over c. It's a one-dimensional integral, right? Because a curve is a one-dimensional thing. And we have a function defined, it could be defined everywhere in space, but we're only evaluating it for points along this curve. And then we write ds. And we call this, unfortunately, in my opinion, we call it a line integral. The better name for it is a path integral, and you do see that, but people say line integral quite a bit, even though the curve doesn't have to be a line. So anyhow, given the way to calculate one of these line integrals is to integrate as a function of t. And then if you like, you could write ds as ds dt times dt by the chain rule. So substituting in what ds dt is and making this a little bit easier on ourselves, let's just write f of r. Okay, so we know we plug in x, y, and z here. And then this is magnitude r prime dt. Now the way we've done this, the result depends on the curve. But not on the way we choose t. So remember, if you think of t as being time, by walking along the curve at different speeds as we go, you could get different parameterizations of that curve, but they all give the exact same line integral when you use this formula.